So the next talk is by Professor Pallab Singh Mahapatra. He is an associate professor in the Department of Mechanical Engineering at IIT Madras. So he received his PhD from Jadavpur University in 2014, and he was awarded the Early Career Level Institute Research and Development Award in 2022 and V. Ganeshan Faculty Fellowship of IIT Madras in 2023. His research interests include surface engineering and wettability patterning, open surface microfluidics, multi-phase flow, and collective dynamics.
Okay, good morning everyone. So today I will talk about slightly different things. From the morning we have seen very exciting talks. So after Rishi and before that we have a very nice talk on heat pipes. So I will talk about slightly on the heat pipes, and then we will move into thermosiphones. And this talk will mainly on the performance improvement. So I will not talk about the fundamentals of it because you already have known it. So this work was done in collaboration with Professor Arvind. So we worked together in this field for quite some time now. So as this workshop is mainly on heat transfer enhancement and on the devices, how we can use it for different thermal transport applications. So we will see what is happening for the electronic cooling. And if we have seen the talk by the person from Intel, that there is already a demand of higher heat flux removal from the electronics chip. And if we see the failures, more than 55% failures of the electronic chips are due to the temperature or the high temperatures. And if we see what are the what are the solutions of removing these heat transfers, we can start with say natural convections, and finally the highest heat flux coefficients we can get is from the boiling and condensation. So we can use a device which can have these boiling and condensation phenomena together, and the possible solutions for that is heat pipes or thermosiphones. So these heat pipe and thermosiphones use boiling and condensation, as you have already seen it before. We will talk about the modifications of that, like if we change the wetting conditions of these heat pipes or the thermosiphones, how we can improve the performance further. And before going into the wettability or the surface modifications, first I will, as there are many students, first I will define what the wettability is. So when we are talking about the wettability, we are talking about the liquid spreading on a surface, and we define a contact angle. This contact angle is when you put a droplet on a surface, the angle it creates at the three-phase contact line is the contact angle. So which we are showing is as theta. So this pointer don't work here. So this is theta is the contact angle, and we as I said, we define the contact angle like this. This is a classical Young-Laplace equations where the surface energies are related with the contact angle. And depending on the surfaces, a liquid can form different types of configurations. If a surface is hydrophilic, which is the last configurations here, the liquid will spread on the surface, and we call it the fully wetting. So if the liquid completely spread the surface or contact angle is close to 0, we call this surface as superhydrophilic. If the liquid makes an angle close to 90 degree, less than 90 degree, but more than 10-15 degree, we call it hydrophilic surface. If it is more than 150 degree, we call it a superhydrophobic surface, and more than 90 is the hydrophobic surface. So today I will talk about all the works mainly done by our students, mainly Praveen, Laxman was a postdoc, and then Hemant. So we will talk about their work mainly, and there are two more definitions which is required. One is advancing contact angle, another is the receding contact angle. So when you put a liquid on a surface, this is a way to measure the advancing contact angle, and now if you tilt the surface, it will create two different angles, one is in the front, one in the back. and we call the front angle is the advancing contact angle, back is the receding contact angle. And to measure that, generally we put liquid on a surface and then we pump it and we measure the angle when it is advancing. And the similar way, if we try to recede the liquid from, we try to withdraw the liquid from the droplet, then it will change the diameter and we call it the receding contact angle. So, the difference between this advancing and receding contact angle is called the hysteresis of the surface. So, with this background, I will start the discussions on wettability modifications on the devices. And this contact angle hysteresis, depending on how we are creating the surfaces, it can be very high, like 10 to 50 degree, or if we make a superhydrophobic surface with a very low contact angle hysteresis, it can be below 5 degree. So, first I will start with a pulsating heat pipe, what we have seen in the morning today. So, this is a working principle of a wick based heat pipe, where you have a wick and the liquid will evaporate, it will go towards the condenser, it will come back through the wicking. And if you have a pulsating heat pipe, pulsating heat pipe can also be of two types. One is a capillary tube pulsating heat pipe, where you have a capillary tubes and liquids, vapor plugs and liquid slugs will move, or it can be a flat plate pulsating heat pipe, like the one you can see here. So, it is like a flat plate where microchannels are cut into it, and you have a heat pipe. It is like a plate where you have evaporator sections, you have a condenser sections, and in between you have adiabatic sections. So, this contact angle or the surfaces have different roles, particularly in boiling and condensations. So, this video should play. Okay. So, it is playing. So, if you have a very low contact angle on a surface, so your bubble dynamics will be different in a boiling conditions as well as in a condensation scenario. Yep. So, this in a condensation scenario, the first figure is a film wise condensation. If your surface is hydrophilic or superhydrophilic, you will see a film wise condensations. If your surface is hydrophobic or superhydrophobic, you will see a drop wise condensation. And there are different modes of condensations. Here I am showing a jumping induced drop wise condensations, which you may not see in these devices in most of the cases. So, this is like two droplet coalesce and then it will jump off from the surface. If you do condensation experiments separately, you can see this. And in the flat plate pulsating heat pipes, we can modify either the evaporator or the condenser. So, generally, or you can modify the whole heat pipe itself. What we did, we have taken a bare surface which has contact angle around 78 degree. We modified with a superhydrophobic, like completely superhydrophobic, all the parts are superhydrophobic. Even we have done with all the parts are superhydrophilic, and then we have done a partially like superhydrophobic condenser and a hydrophilic evaporator and adiabatic sections. And we have seen the performance, how it is changing. I will not go very detail about it because you have already, Marco has already discussed the heat pipes. So, I will just talk about how we can modify surfaces little bit, so that if you, there are students, if you want to use these modifications techniques, you can use. These are not very difficult to do. These are mainly chemical based techniques. So, if you have a copper based, these are all copper based heat pipes, flat plate pulsating heat pipe. So, we have taken this copper flat plate pulsating heat pipe, we polished with sandpaper, then cleaned with ethanol and DI water, then we cleaned with nitric acid, then we immersed it with sodium hydroxide and potassium persulfate for certain time, dried in hot oven, then we got a superhydrophilic pulsating superhydrophilic surface. Now, if you use in a FAS, so which is we have talked about PFAS yesterday, that it can be ban in some time, but we have currently we are using fast. We have also used some other techniques where you don't need any agents to create superhydrophobicity, but we have not applied anything on this yet. If you are interested, we can talk about the other methods of creating superhydrophobicity on surfaces and so on. Then if we create, if we dry it, we will get a superhydrophobic surface. So we will get contact angle around 160 degree, and our hysteresis is also very low, is less than 5 degree. So this is one way of creating this. So after doing this, so we have seen this is corresponding to 60 watt how the behaviors, and we have seen this best thermal performance that we got is when we have a superhydrophilic, they call it superhydrophilic, and we got a better performance and so on. So with this, I will go to thermosiphon, where I want to discuss more rather than the heat pipes. So we have worked on thermosiphons. Basically, there are different types of thermosiphons. Thermosiphons, as today also Marco mentioning, so thermosiphons is also something similar to the heat pipes, particularly if you have a cylindrical thermosiphons, which is almost similar to the heat pipes, but there are other thermosiphons, say loop thermosiphons or vertical plate thermosiphons. We have also a horizontal flat thermosiphons, or it's a compact, these are compact, and these are more suitable for cooling electronic devices. Even if you have a multiple heat sources, you can use this type of compact flat thermosiphons to cool it down. What we used is a thermosiphon and with a heat source. This is our initial works, and we use a kind of a complex flat thermosiphons, we call it CFT, and we change the surface conditions. We have used hydrophilic evaporator, superhydrophobic condenser, also we used different types of combinations, and we want to see how this performance changes with these modifications. So our objective is to study these compact flat thermosiphons at different filling ratios, working fluids, and different heat sources. Then we used these sweatability modifications on the evaporator and condenser to see how this behavior changes. We have also modified this condenser to have a hollow fins. So instead of a flat condenser, if we have a hollow fins at the top, like how this behavior changes. So we have created a integrated flat thermosiphon heatsink which has a hollow fins. So we will see how that behavior will change, and also we have added a micro channel in the evaporator sections to get the benefit of both the sides, both the evaporations as well as the condensers. So the objective of this is to study the thermal performance of compact flat thermosiphons for different filling ratios and working fluids, see the behaviors of the wetting characteristics, and then this for enhanced performance, how we can use this hollow fin type of structures. So to start with this compact flat thermosiphons, this is our schematics, this is the actual setups. I will just skip this. Maybe we will start with the experimental process. So to understand what is the heat flux, the main problem of using these closed devices, you cannot see what is happening inside. So we can understand the outside, mainly the temperature data. We don't know exactly what is the heat flux distributions inside it, and also how the let's say how the bubbles are departing, how the bubbles are coming out from the evaporator sections, and how it is condensing and so on. So we can do separate experiments, which we did to understand the fundamentals of it. And then there are other techniques, like if we can somehow predict the heat flux on the inside surface and so on. But here what we did, as we have multiple thermocouples inside the heated block, from there with a 1D Fourier law we can predict what is the heat flux we are giving at the evaporator surface. Then we can characterize the total resistance, which will indicate the device performance. We can calculate the spreading resistance, which will indicate the heat spreading. Then we can calculate the evaporator resistance, which will indicate the boiling heat transfer, and finally the condenser resistance will give it the condensation heat transfer. So these are some indications or indicators of our device. Okay. Then we can have the resistance map and so on. So if we see what is the effect of the working fluid, we have done experiments with acetone, water, ethanol, and we have seen how these behaviors changes. So we have seen that evaporator maximum temperature at I think 40 watt per centimeter squares, we have a highest temperature for ethanol and lowest temperature for water. The maximum temperature at the evaporator, if we are seeing this is, so we are seeing the maximum temperature for ethanol and the lowest for the water. So if we see it from the performance of it, from the resistance, total resistance, if you see, water is having a lowest resistance. However, there is no significant difference on the spreading resistance, and the evaporator resistance also water is the lowest, and ethanol is having a higher evaporator resistance, and from the condenser resistance also water is the lowest. So with all these, we have identified that water is the best working fluid due to its low vapor pressure and high latent and specific heads. So for these particular conditions, without any modifications, when we are doing it, we have seen that water is performing better than ethanol and acetone. Okay. So then we have also studied what is the effect of filling ratios. So we have studied with 20%, 50% and 80% filling of the thermosiphon, compact flat thermosiphons, and here also we have observed, let us say this is if we concentrate on the middle graph. So the spatial resolutions, you can see that the maximum temperatures we are getting for 20% is more than 90 degree, whereas for 50% it is like maybe 75 or something like that, and this is for 30 watt per centimeter square. So what we have observed is at 20 when the filling ratios is 20%, it is more than the 80% and the 50%. So I will come to that reason here. So the total resistance, you can see that 50% is having a lower resistance, and 20% will have a higher resistance. Similarly, your spreading resistance is also similar, and the evaporator resistance and the condenser resistance is also showing the similar thing. So when we have a 20% of filling ratios, then we have a less working fluid, and that deteriorates the performance. Whereas when we have a very like filling ratio is very high, like 80%, then it is giving a flooding type of situations, and that deteriorates the thermal performance. Whereas 50% giving the best performance, but it we are not telling that 50 exactly it is the 50% is the optimum, but it is better than these three, like in these three conditions. Okay. So to understand the physics, how it is happening, as I said earlier, so we have to do some kind of numerical modeling only to understand how the droplet is departing and how it will come back and so on. So we have started this numerical modeling of the whole system. So we did a particularly if you have a multiple heat sources, instead of creating another device to test it. So we have done a numerical simulations, but these numerical simulations are also very early stage. We did only 2D numerical simulations. We have not taken care of the effect of the roughnesses or the surface wetting conditions. What we have taken, used a VOF model in ANSYS, and we have used a Lee model to model this evaporations and condensations on the surface. And as this is a multi-phase modeling, we have only solved the secondary phase, and the primary phase we have subtracted from 1 and we got that. So then this is the surface reconstructions. I will not go detail of it, maybe we can discuss it separately. So these are the conditions, and we have done only a 2D simulations. We did a grid independent studies, and I will show you, yeah. So comparison of our experimental results with simulations. So if we see the experimental and simulations results of the total resistance, the trend is similar. It's not that it is exactly matching, but the trend is similar, although we have 14 to 20% of deviations from the experiments, but we got the overall idea how the bubbles are moving from one surface to another surface, and it's coming down and so on. And we got the overall trend of resistance, we got the overall trend of spreading resistance. Even we have many informations like the pressure, local pressure, local temperature distributions, heat flux and so on. So we will get lot of other informations that we otherwise not get from the experiments. Even we did some work on when we will have a multiple heat sources rather than a single heat source, so on. So now if we do the wetting modifications, so far we are talking about without modifying the surfaces. Now if we do the wetting modifications, this method is also similar because we are using the copper again. So I will just skip through it. So we have the similar method, but with this we have created different types of flat plate, this CFT, flat thermosiphon. So we have created actually 5 CFTs. So in one case we have CFT1 is both the bare, that is bare copper, both are hydrophilic. Then CFT2 is your evaporator is hydrophilic and condenser is superhydrophobic, and CFT3 is superhydrophilic, superhydrophobic, and we have superhydrophilic, hydrophilic, as well as CFT5 is both superhydrophobic. Then we compare the performance of it, and what we have observed is, if you see CFT5, when both are superhydrophobic, we have seen the evaporator temperature is very high. And if we have CFT2, where we have a evaporator as hydrophilic and condenser is superhydrophobic, our performance is better, and the temperature is much lower. It is around 60 degree compared to 120 degree. So this is happening because we have a superhydrophobic condenser where we have a drop-wise condensation, and that improve the performance of the overall system. So then we have measured for different heat, we did experiments with different heat fluxes and so on. So this is the same thing what we are seeing in the graphs. Okay. So now this is from the resistance map. You can see the similar behavior you will see here. The total resistance for the CFT2, where we have a superhydrophobic condenser, is lower than the all superhydrophobic. Okay. Yeah. So CFT5. So CFT5, as it has a superhydrophobic condenser, so it is in between from the condenser resistance, but the overall resistance is much lower for CFT2. Okay. So if we see now our understanding, whatever we have seen in the previous one. So we have CFT1 where the baseline are unmodified, and we have CFT2 where is hydrophilic and hydrophobic. We have best performance 1 because condensation is enhancing because of the superhydrophobic condenser, and CFT3 we have a superhydrophilic evaporator and superhydrophobic condenser. So our performance is better than CFT1 because condensation is enhanced more than the boiling deteriorations, whereas this performance is worse in CFT4 because this boiling deteriorates because we have used a superhydrophilic evaporator, so there the boiling is not working properly, whereas in CFT5 this is the worst performance one, as boiling deteriorates much more than the condensation enhancement. So that's what is happening. So what we have seen that superhydrophobic condenser improve the condensation heat transfer through dropwise condensation, and that quickly returns the liquid to the surface or to the evaporator, and that improves the overall performance. Okay. So then we started seeing that can we improve the condenser surface with a fin. So we have done three types of experiments. One is compact flat thermosiphons, what we have shown earlier, as well as there is a solid fin and there is a hollow fin. So this is this is the experimental setup, the schematic of the experimental setup. So we have used the similar overall resistance, spreading resistance, evaporator resistance, condenser resistance to understand it. So this is the configurations we are comparing. So first is the condenser without any fin, then condenser with a solid fin, and then condenser with a hollow fin, and we want to see how the performance changes. So yeah, I have 5 minutes. So here we can see that when we have no fin, so the temperature is higher compared to when we have a hollow fin. So evaporator maximum temperature went up to 136 close to, and here it is close to 90 degree when our heat flux is close to 30 something, 30 watt per centimeter square. So no fin temperature of the no fin in the evaporator is greater than the solid fin and the hollow fin. So what we did afterwards, we will see the overall resistance. It also shows the similar behavior. It also tells us that the hollow fin performs better than the no fin conditions. However, there is no significant difference in the spreading and the evaporator resistance, and the condenser resistance, no fin and solid fin, is almost similar than the hollow fin. So condenser with integrated hollow fins like this designs, this performs better due to a better vapor distributions, because we are having a higher surface area, as well as it is a better drainage from the top to the bottom. Okay. So we have also studied the filling ratios. So we have seen what is the effect of filling ratios, 80%, 20%, 60% and 40%. So we did, and what we have observed that I will show through the resistance here. So okay, I think this is similar. So we have seen the 40% filling ratios performs better, because 20% filling ratio is too less, whereas 60 and 80% are too high and it floods. Basically it actually decrease the overall condensation areas when you have 80% of filling ratio. So schematically, if you see, 20% filling ratio is too low, and 60 and 80% it is actually even flooding the condenser areas. So we have to do an optimum filling ratios, only then you can do it. So we have seen that 40% is filling ratio is best performing filling ratios for our conditions. So being said that, we have studied only a particular type of geometries, we can do lot of improvement here. There are a lot of optimizations required, what is the spacings and what is the size of it and so on. So we have shown it that yes, it is possible to improve, like if you have a hollow type of structures, which will have basically you are giving a more condenser areas. Okay. So then we were saying, okay, now if we improve through the surfaces, we modify the surfaces. So we have used that design with a bare evaporator, bare condenser without any modifications, and then bare evaporator with a superhydrophobic condenser. Then we have a mini channel evaporator and a bare condenser, as well as we have a mini channel on the evaporator and a superhydrophobic condenser. So we did all these combinations and tried to see how we can improve the performance. So, superhydrophobic surface creations are similar, which I was talking about. So, bare copper is around 78 degree and superhydrophobic surface is close to 160 degree, and we have a mini channel evaporator. I will not go into that. So, overall what we have seen when we have this we have taken the advantage of the mini channel evaporator and superhydrophobic condenser, it performs better than the bare evaporator and condenser, so which is expected. So, we got that, and this has been also reported, or we have also identified that through the resistance map. Okay. So, what we have seen that superhydrophobic condenser improved the performance by 16% due to the quicker condensate return from due to the drop wise condensation, and the mini channel evaporator improves almost 19%, and if we take both the advantages, it is almost 36%. It is not additive, but it is close to 36% improvement if we do that. Okay. So, in conclusions, what we have identified is, in our system, what is the best performant working fluid due to the low vapor pressure, high latent and specific heats, and safety is more reliable than single phase cold plate cooling, particularly for multiple heat sources, and this can be improved, the CFT's performance can be improved through wetting modifications, although there will be questions of the durability and other things, but these are possibilities that we can improve the performance. And particularly with this integrated flat thermosiphon heat sinks, what we have observed that it performs better due to more condensation areas and with the same footprint of the inner volume. However, the superhydrophobic condenser surface enhance the performance due to the drop wise condensations. So, this is there. So, combinations of the mini channel evaporator and superhydrophobic condenser is the best performing device for us. So, with that I want to conclude, but the final notes is we can, so these are all thermosiphons. We can work on this will not work, as Marco was also mentioning, this is not gravity independent. So, so if we want to use it in a outer space, we have to use vapor chambers or some other techniques what Rishi was mentioning. So, and also for a very smaller space, we have to use micro mini vapor chambers. So, that there are already some vapor chambers people are working on with a micro vapor chambers and so on. So, currently we have used only homogeneous wetting modifications. So, we have not tried with a biphilic surfaces or patterned wettable surfaces. When we are talking about a patterned wettable surface, it means we have a juxtaposed surface of different wettability. So, we can create that enhances droplet transport, movability and so on. So, we can try for patterned wettable surface on the particularly on the condenser, that will remove the droplets even easier, and then we have to use it for actual cooling applications. So, the sizes of these systems definitely matters, and the particular designs, how you can use it for those applications, we have to take care of that. And sometimes depending on the applications, particularly what Marco was also mentioning, and there are few works particularly on the battery thermal management, where you cannot use only one type of systems, maybe vapor chambers and heat pipes can be work together. So, this is one example where one group has used vapor chambers and thermosiphon, vapor chambers and heat pipes together to do a battery thermal management. So, with this I will end. Thank you. So, yeah. Yes. I have. Yeah. Yeah. Yeah, we can mask and do that. So if you have channels, particularly in a heat pipe case, then it is slightly tricky. You have to probably mask it with the channels. Let's say probably, let's say you do a wax coating or something like that, and then or some colors that will again dissolve with some other liquid or some other chemicals that will not change the wetting conditions of the other part. That can be done.
If photolithography is so complicated, this is probably
Yeah.
something that we can adapt from.
Yes, yes. Like
So I had a remark and a question, but I think I'll start with a question and then give the remark. So when you're showing, heat flux and resistance, condensator and evaporator, I noticed they're often highly nonlinear.
Yes.
Probably the most nonlinear was slide 24, if we could look just briefly.
Yeah.
And so you gave a lot of integral results, but you never talked about the physics.
yes,
Could
yes.
you,
And that's what
what's going on? Why does it go down and then flatten out? What's physically happening? Or
So-
on the on the evaporator, it's even more nonlinear.
Yeah, these datas are non-linear. I completely agree. Honestly speaking, it's not that we also understood it. Yeah, so it saturates. So what happened particularly when you have a very high heat flux? So particularly, let's say this case, at a very high heat flux, you have a more water vapor and it condenses. So when you have a lower heat flux, there is a possibility and what we did, we have changed the heat flux. It's not a continuous heat flux. We are changing the heat fluxes to go up to that level. So when we said we reached a steady state for a certain time, and then again we change the heat flux to go into the next level and so on. So one possibility here, what I can think of is we have the condensation behaviors after that heat flux. The number of the vapor that we are generating is almost uniform, like almost constant. The whole surface is having a similar behavior. So then your resistance, overall resistance, is not changing that much.
Yeah, that explains the saturation, and
Yes,
your
yes.
coverage is 100%, but it doesn't explain
Yeah,
what's
I agree.
going down.
I agree, and that's why I said there. Why this curve is like this and why that is slightly other, I don't know.
Okay, but you have to understand that before you
yes,
can
I
start
agree.
start explaining your integral results.
So that's
The
why
remark-
we have to do because we cannot see anything.
I understand.
So we have to.
You can
yeah.
hypothesize.
So
And the remark I had is that it might be more interesting, instead of looking patterned, gradient wettabilities. And I think if you look at the work of Glenn McHale in Edinburgh, he's
Yeah.
doing that very nicely. He's inducing mobility with gradient wettability.
Yeah, no, we also did on a condensing surfaces. So when we can see,
Yeah.
I did a lot of work on that. When you have a surface, we can move the droplets on a. But when it is inside, before going into the wetting transitions, so we want to see how, like probably the next steps. We have also started this. We are also trying to understand it. But yeah, that's a good point.
Yeah, your work is very nice, and I think it is very fruitful for the beginners, for these thermosiphon and heat pipe researchers. See, you have shown a very good way to make any surface being hydrophobic and hydrophilic. So it's a good kind of and very simple and effective method to prepare any surfaces being super hydrophobic and philic. I would like to just know that what is the longevity of the surface being treated as the super hydrophobic and hydrophilic.
So super hydrophobic surfaces are longer. Super hydrophilic surfaces are slightly tricky, particularly when you are not in a closed system like this. If you have a, like, let's talk about when you are talking about a aging or durability of the surfaces, we did some work. So super hydrophilic surface is a very high energy surface. So it will absorb hydrocarbons, it will absorb many other things, and it will change these wetting characteristics. So you have to store it properly. When it is in a closed system, it works. it
No,
works for a long time.
I want to
So-
put the question that way, that suppose I'll prepare one surface within this method, how long will it be under the...
No, that's
yeah.
what I was telling.
Yeah.
So how you are keeping the surface?
Okay.
So if your surface is, you kept it open, it will absorb
Okay,
hydrocarbons and
okay.
other things, and it will change, it will increase the angles.
So it has to be
I
kept
think
in
we
the
will discuss
enclosure.
this
Yeah.
outside because
I
we are
think we
running
can
out of
discuss
time.
this just after.
Because this is a long
Yeah, when
thing,
we
yeah.
have the lunch,
Yes.
we have a long session.
Yeah, we will do that. But this is a good
So-
point, yeah.
I request maybe Professor Tropia now this time to hand over the memento to Pallav.
Ha.
Okay, to my best friend.
Yeah.